Most of you have probably used AI assistant like ChatGPT, Claude, Gemini, Grok, DeepSeek, Perplexity, or any other, like one or more must have used it. But have you wondered what actually happens after you hit the enter, right? A prompt entered the system, and then within a millisecond or second, a response appears. Behind that response lies a complicated system, a more sophisticated distributed system you have built it, right? Request travels through gateway, schedulers, tokenizer, inference runtime, and many more components, GPU clusters, streaming, and then within that, the single token reaches the screen. This is the most complicated distributed system ever built it. Welcome to the Architecting Intelligence, and this is the series for LLM inferencing called Architecting LLM Inferencing. My name is Pawan Jha, and this is a part of one of this series, Architecting LLM series. Today we'll build the mental model for understanding how modern LLM inference system works. Let's go to the series roadmap. This is a 10-part series, and this is the first part. We're going to give something like end-to-end or more of foundational. We're seeing how there's a different component plugged together to make the system works. Before we dive in, let me quickly show you what we are going to the overall journey. This series starts with the fundamentals, and today we'll focus on the complete inference lifecycle. In part 2, we'll go inside the runtime and understanding autoregressive generation, schedulings, and then executions. Right. In part 3 of this, this end-to-end part, they will focus operating LLM at the scale, how to optimize, how to make it security layers around reliability, monitoring, and productionize it. Part 1 will cover today into this video, and then 2 and 3 will coming soon. Before we begin, I want to quickly explain few logistics, how we organize the things. In Substack, you will find the detailed research article. We'll try to cover the concept part in the YouTube video, but there are many other things that we can't do here, like more of the detailed research, mathematical stuffs. You can subscribe to my Substacks for that. And then YouTube, I already talked about. We'll go to the deeper explanation of the concepts. And then GitHub also is there where we coding part, like when we write code or few implementation, that will share the codes on the GitHub. So subscribe there. And then we'll also have a Twitter account, like we're X account now. So where we're publishing research idea, where I think that things can be taken as the next level, or things can be do differently. So those people are interested in research ideas or interesting papers, industry trends, they can subscribe there, like thought that eventually whatever my thought of those direction comes, I generally put on Twitter. So if you are interested on those research areas where we can build, optimize in that direction, do subscribe on the X. Together, this platform found the Architecting Intelligence Learning Ecosystem. So if you read these 3-4 systems, if you subscribe and go through, then you will get a complete detailed. One thing I want to highlight, this whatever we are producing here, you will not find anywhere actually. These large companies like OpenAI and Anthropic, they never disclose how their inference or how their training infrastructures work underneath. Those are very hidden, and most of the speculation piece or few articles or paper comes and then people speculate. But here we want to give you some sort of how large scale inference, or when we go compare go through other series, how things are working in the real. So you can, if you are working on the design part or architecting those large scale system, or even implementing it, or even some part of the things you are doing, so that give you complete pictures at how the large scale ML system works or AI system works. And one more thing, so before we begin, throughout this video, I will raise some questions, right? When we go somewhere, some part, I will keep raising some questions, and this is just to get some sort of thought process for you. So treat them like a small assignment, and pause, think about the scenario, and share your thoughts in the comments. And many of these will be revisited in the next part of that video, or the series will come. Then we'll answer some of those questions. Those questions will give you some sort of thinking process to start, that this can be done with that can be optimized that way or not way. Where is the bottlenecks? Where can be failures? So those things keep in mind. Now with that, let's start our journey into LLM inference. Now, many people ask that why ML engineers or ML scientists should take care of the inference. So we'll go into the importance of the inference. Before that, I just want to give you some sort of life cycle of the modern LLM systems. If you see the left side of the diagram, it's talking about the modern life cycle, and here the inference that the arrow is that is actually highlighting the inference rate. There are different types like pre-training, and then where we have mid-training, where you curate data and then train, and then some sort of mid-training with the specialized training where you do the context sizing, increasing context sizing, or with the synthetic data. And then you do evaluation where you do benchmarking on certain tasks of your models, and then you publishing those benchmark tasks, that how the models are performing. And then there is a series of called alignment, that there is a word for that, something called post-training, where you align this model, whatever you learn it, to certain tasks, either domain related task or safety related or privacy related. And then again, these are tasks, these alignments are different direction. One, we go at it like the correctness, where we given tune with true correct versus incorrect, and then better humane in preferences based, like one preference versus other. So there is a big series that we are coming up. You can check my Substacks where we trying to run about that post training, where 2 part is already published, and then video is also coming where we'll talk about the supervised, how this RL based reinforcement learning burst in the LLMs. Okay, now let's focus on why ML engineers should care about inference. Traditionally, machine learning education focus heavily on model training, but in production, inference is where organizations spend most of their operational budget. So every user request trigger inference, every token generated consume compute resources, and every millisecond of the latency affects user experience. As ML engineer, we need to think beyond model accuracy, and we need to understand deployment, latency optimization, GPU utilization, cost efficiency, monitoring, and reliability. Modern AI products succeed not only because of the great models, but because of the great inference system. So I told about, I generally keep telling that inference decide how your AI product will pass or fail, because so many directions are there, so many dimensions are there. And if you are not build a good inference infrastructure or good inference systems, even you have a good models, and if suppose your latency is not good, security systems around not good, hallucination, truthfulness, or the way you model tracking, right, and the cost part, these are you're not within that acceptable things, then maybe your overall things are not working out, or overall whole product will fail it. Now let's go to the part that why inference is hard. Now you must have got idea that inference is a really complicated engineering problem. There are many things to optimize, or many dimensions these things are going on, and you need to optimize it. For example, inference is hard because of the latency. At a glance, inference sounds simple, but load a model, send a prompt, generate response, but it really much more complicated. You need to balance all these directions. Like we want low latency, we want high throughput, we want high availability, low cost, we want efficient GPU utilization. So the challenge is that improving one metric often hurts another. So it's like these all are going different direction. So how to build a system that where all can optimize it. So this becomes a sort of optimization problem also. So challenge is the improving one metrics, but without hurting to another. So for example, larger batches improve throughout, but increase latency. If you increase the batch size, right, but they increase the latency use. So throughput will increase, but latency will increase, right? This is why inference is involved with distributed system problem. So inference is not only ML problem, it's like more of compute, memory, hybrid, all this together, and then ML itself, like how you can optimize your models in inference time. So there is ML part, there is a system engineering part, there is distributed system part, and then whole ecosystems around that where they are combining together. So therefore, it's a difficult actually, and you need a right set of a skill set for to build a highly scalable inference system. So I want to go request lifecycle to make you feel right how when you have first question I asked that how you prompt it and get the answer, what is happening behind. Let's think that right. Let's now follow a request through a production inference system. Imagine a user submit a prompt. The request first reaches an API gateway, and then the gateway perform authentication, rate limiting, and traffic management. That as usual. And the API gateway does it, right? And then request them move to model gateway and model router. These services decide which model should handle the request. There are many models, each model has different version. So which one need to pick, or which types of request, is that image focused model or is text focused model? Within that there is many variants. So these two component, gateways and order, together decides, right, which model need to be picked with and which version need to be picked. Next come is tokenization, right? When readable text, you put a text in the prompt, that need to be converted into token ID. So what is a token ID? So before that is like convert into tokens. Like first you convert like bird, split these whole sentences into words, and then there are different tokenizers. So we'll deep dive in the coming series. But think like this stream need converted into tokens, and these converted tokens need to convert it some sort of ID. Now how to convert into ID? You need to convert a vocabulary. You manage a dictionary, and each dictionary has the position values. Like book becomes something, and that's a corresponding ID generation, we call it. So you convert this token ID. So end of day tokenization, you have bunch of IDs, bunch of unique numbers. Then these need to be converted into some sort of embedding that we call scalar to tensor or multidimensional vector converter, and that request then sent to inference runtimes such as BLLM on tensor RTLLM, and then runtime schedule works across GPU. Then there is a schedulers, and then batching. Whole model works on that and get the next token. This model generate tokens. Those tokens are converted back to the again as a prompt. Like therefore we called it auto-regressive model. And finally the response is streamed back to the user. Everything we discuss in this series fit somewhere within this life cycle. Within these steps are deep dives. So we'll go in coming videos. But think like a broad level. These 9 steps make your response perfect. Let's go to the one example. Let's make this concrete to understand you better. So suppose your user asks, what is the capital of France? The browser sends a JSON request to the backend, and then application server validate the request and perform the authentication check that this is a valid request. The text is then tokenized. For example, what is another token, is become another token, the become another token, capital become another token, France is become another token, right? So these are the token, and then I talked about that this to convert it into token ID. So lookups, right? There are the vocabularies they manage. So every model they manage their vocabularies, right? And therefore it's a multi-model or multi-language, their vocabulary are different. Those model are English-based model, their vocabularies are different. So these token ID sent to the model where the first layer is you do embeddings. So where you convert this token into multi-dimensional vectors. This model predict the next token. So eventually it generates something like Paris. What token is converted back into text and stream into the user. So this is a basically give you to the one prompt how it converted. But within runtime, here I just touched that up the token you just sent to the runtime token ID. But there are complicated steps there in bit. That is just something like we'll go to the part 2 of the videos, that how this token ID you just give, then complicated setup of steps run over that and you get the response. All the answer seems simple, but the large language system participate in generating that response. Now let's go to the transformer. These are the models are basically a transformer model, or mainly these are decoder based model. So let's go to the inside the transformer. You see the first step, that token ID, that I think you must have got idea now. The text, the tokens to token ID we generated. And then this become a sequence of tokens. Then this sequence of tokens converted into scalars, right? I raise a question here. Why you think that we need to convert this text to text ID? So that is a question number one. How to convert, or why you are converting first is scalar token ID to some sort of a tensor or multidimensional vectors, right? Why you need that? This is a question 2. And then question 3 I want to ask, how you can convert a scalar token ID to tensors. What are the different ways? Note this question in your mind and put the answer in the comment. Now you got a token embedding layer. Earlier there is also concept called positional embedding, where you combine token embedding with the position, that where this token lies in the prompt. But now in the modern LLM, that push into some sort of a attention layer itself, where you this positional embedding or merge with the attention layers, and then some sort of rotational matrix you create, or some sort of like rope and a Libby types of algorithm you put. So therefore I'm not putting here some sort of positional embedding. But if you see the earlier paper, then there is also concept called positional embedding, where that positional embedding you create, that is basically most of the based on the position of that token in the prompt, and then you combine, add together, and then make some sort of final before going to the attention layer. But here in modern LLM, that will push server. Therefore, I just leave it there to token embedding. And then there is n transformer layers, right? Each layer performs the attention calculation, and then there is a feed forward. If you little unpack that, if you see there is every transformer block has a first step is a something called a layer norm or normalization, normalize your weight so that your gradients are not exploding. So layer norm generally we use, and then you do a multi-head attention, and then you do dropout. But inference time you don't do dropout, mainly training time. And then you put a connection, the input, we call a residual connection. And then you put a feed forward network with the linear layers. So again, before linear layer, you need to normalize. This linear layer works. And then again, you need to put the residual connection. So there's two blocks actually within that block. One is the multi-head attention block. One is the linear block, together packed as a one transformer block. There are n of the transformer together. So this X, like input going through that, it is going, X is converting so many transform block. And end of day, there is a one linear block that has a something like, that is also feed forward network. And after that is a softmax layer, which converting to the probability of the possible tokens in their vocabularies. And then you have a decoder. You pick the next token on the basis of your decoding strategy, like beam search or top K or top P, depending on how you're selecting the probability or top K, or there are different speculative decoding. So we'll go there, but think like to select that token for now. It is token 1 or whatever the first token you selected. Suppose the highest probability you selected the token, or highest frequencies of the tokens, whichever the coming that you selected, and then put that tokens to the prompt itself. So it's become a auto regressive, and then next token and keep going. Now I have a question for you. Where you think that that we need to stop it, right? And which component is going to decide, and what will happen if that is not a correct stop, right? How you find out how to judge it, right? That is the right end of token has been reached. So this is for you to think about that. What are the best way to analyze the end of tokens? Let's go to the next. This is something like a token generation pipeline. If you combine what we just study, we have a token, then token sequence, then embedding token, then n transformer block, then linear, and then selecting the token. And then again, you got a vectors, need to go to the scalar, because end of day, you have to again back to text. So this like reverse, whatever you started with that, right? You got a token ID. Now you need to look up for the vocabulary table and get the next token. And that will keep going till you get to the end of token. So this is a basically whole token generation pipeline. Now, there are many failure points, scaling point, failure point, optimization point. Now you have to come and note with that where you think that system get wrong, right? We will cover in the next video, but I just think that I just give you broad level connection point, plumbing point. Now you think where can go wrong, and what do you think that how to solve this thing? This is a next question that I want to put it here in this video. I want to touch one more topics in this, or maybe I will save this for next videos, because it's already longer video. So I will end it there, and then latency and other I will take next part of video. So thank you for the watching it. I request to subscribe it, the different ecosystem talk. Okay. Thank you.